one more talk this afternoon. It is Pretreatment and Activity of Iron Fischer Tropsch Catalysts, and it is co-authored by Bob Obrien, Lee Wong Chu, and Bert Davis. And Bob Obrien will give the presentation.
Well, today I'm going to be presenting some of the results of our studies on the impact of pretreatment on the activity and phase composition of precipitated iron catalysts, which are used in the slurry phase Fischer Tropsch synthesis. Well, the slurry phase Fischer Tropsch process, finely divided catalyst is suspended in a high boiling hydrocarbon oil, usually preferably a Fischer Tropsch wax. Synthesis gases simply bubble through the reactor. Volatile products and unreacted synthesis gas exit through the top of the reactor. Heavy products, which accumulate in the reactors, are removed through some sort of a filtration system. These types of reactors, the slurry reactors that is, offer several advantages over conventional fixed bed reactors, namely that they can handle low hydrogen or hydrogen-lean synthesis gas without fear of plugging the reactors with food-water carbon. Also, you get much better temperature control, and they're simpler to construct and much less expensive. The most comprehensive study of an iron-based catalyst in a Fischer Tropsch or in a slurry reactor was conducted by Kobel in Germany just after World War II. He operated a fairly large pilot plant which produced over 11 tons of hydrocarbons per day using these conditions. His results were fairly remarkable because he obtained, while operating at a very high conversion, was able to produce high selectivities of gasoline, but accompanied with very low production of undesirable methane and ethane. With increasing interest in Fischer Tropsch synthesis, his results are considered to be a benchmark which, to the present, have not really been completely reproduced. At the CAER, we've been involved in a fairly extensive project to develop a precipitated iron catalyst which is capable of meeting or exceeding the results of Kobel. The project has roughly been divided into three parts. The first of being finding the optimum levels of alkali promoters and supports. And the second and third, which I'll be discussing today, concentrating on the appropriate catalyst activation procedure, that is using CO activation or syngas activation, and catalyst characterization to, if possible, identify the active phases of the reaction. Both of the catalysts which I'll be discussing today were prepared in a continuous mode by precipitating aqueous ferric nitrate with ammonium hydroxide, or precipitating ferric oxyhydroxide from aqueous solutions of ferric nitrate and ammonium hydroxide. The slurry was then pumped into a vacuum drum filter so that it could be filtered continuously. Usually we do 2 washes and 2 filters after the initial precipitation. There's two catalysts I'm going to be discussing today. One was a 10-pound batch, which was just oven dried following the final wash, and was then impregnated with potassium. The second was a rather large 160-pound batch, which, following the lengthy filtration and washings, was re-slurried, impregnated with potassium nitrate, and then we hauled it to UCI to be spray dried and then calcined to 350 degrees. These are the compositions of the two catalysts, and throughout the talk I'll just be referring to them as the 10-pound batch and the 160-pound batch. It's just a simply promoted catalyst with small amounts of silica to act as a structural promoter. And this is the schematic of our slurry reactor that you saw earlier in Ajay's talk. The only thing I'll add is that we've also equipped the reactor with a sampling tube so that I could take catalyst slurry samples periodically during the pretreatments and during the synthesis. In terms of activation, cobalt and ruthenium are fairly straightforward. They can be activated by simply reducing hydrogen to the zero valence state. Now with hydrogen, or with iron rather, the effects of pretreatment are not as clearly understood. Usually the pretreatment is either by reducing its hydrogen, CO, or syngas. In all three cases, the catalyst, usually starting off as hematite, is rapidly reduced to magnetite, usually within 1 to 2 hours. Now with hydrogen as the reducing agent, the magnetite will then slowly be reduced further to alpha iron. But with CO or syngas, usually after extended pretreatments, the catalyst will become usually Hague carbide or epsilon prime Fe2.2C carbides. With hydrogen pretreatment, the resulting alpha iron does not give an initially active catalyst, and an induction period is usually seen in which iron carbides are formed. During the synthesis, operating under high conversions, large amounts of water or CO2 can be formed. So the carbides, which are formed during pretreatment, can then be converted back to magnetite. So unlike cobalt and ruthenium catalysts, which tend to remain in the zero valence state, iron catalysts can exist as mixtures of several carbides and magnetite. And it's not clearly known what the roles of these phases are in the Fischer Tropsch synthesis. Okay, in the talk I'm giving today, the catalysts were essentially the three different types of pretreatment gases. CO, syngas was 0.7, a hydrogen CO ratio of 0.7, and another one was the hydrogen CO ratio of 0.1. All pretreatments were conducted at either 270 degrees C, 13 atmospheres, or 1 atmosphere. And the pretreatments lasted for 24 hours. In all cases, the synthesis was conducted in a similar manner to that reported by Cobell, using hydrogen-lean syngas in 270 C and 13 atmospheres. Very early on in our studies, we found that pretreatment with CO at 13 atmospheres and 270 degrees C gave highly active catalysts, which approached the conversions of Cobell. However, we were not able to obtain his low methane and ethane selectivities, but we were able to exceed his hydrocarbon production. So in all, it seemed like it was a fairly successful procedure. However, since the goal of our project was to develop a process which could be scaled up to pilot plant or even beyond, CO pretreatment is not really desirable because pure CO is fairly expensive. So it seemed logical that you'd want to develop an activation using syngas, preferably with a hydrogen CO ratio the same as the synthesis gas. Now, shown here is the CO conversion for our standard pretreatment with CO at 270, 13 atmospheres, and we achieved very high activities, exceeding 90% conversion initially, and then declining slowly at a rate of about 1.5% per week. But when we went to syngas activation using the same conditions, we found that the catalyst did not really activate. Peak conversions were about 12%. Now, Cobell reported that in his pilot plant, he activated the catalyst at 300 degrees C with syngas at high pressure, 13 atmospheres. I went ahead and tried to reproduce that using our catalyst and did not get very favorable results. The activity only increased to about 20% after about 90 hours on stream. So we had very little increase by increasing the temperature. However, we noticed after quite a bit of frustration, that if we activated the catalyst in syngas at 270 with 1 atmosphere, we got an activity fairly similar initially to that we found with pretreatment with CO. In fact, when we did the 1 atmosphere pretreatment with syngas on our large batch catalyst, we got very good results and have activities approaching 90% for over 1,000 hours. Once again, with this catalyst, even activating at 1 atmosphere, increasing the temperature from 270 to 300 had very little effect on the overall activity. It just appeared that maybe the catalyst activated at 300 degrees deactivates a little quicker. Since there was such a dramatic effect of pretreatment pressure, or pressure on the pretreatment with syngas, we decided to try it with CO, but in this case we found that there was really no difference between activating in 1 atmosphere or 13 atmospheres at 270 degrees C. And this is just a comparison of the large batch catalyst. It was squares would be pretreated at 1 atmosphere with syngas, and circles with CO at 1 atmosphere. And it looked like the syngas pretreatment probably was a little bit better for this catalyst. We were curious to find out if, since pretreating with pure CO gave a highly active catalyst, and pretreating with syngas with a hydrogen or CO ratio of 0.7 gave low activity, what would happen if we used a syngas with even less hydrogen? And what we found is that we get an activity intermediate between the two. And these are both conducted, all 3 of these were conducted at 13 atmospheres. So by decreasing the hydrogen partial pressure, we were able to increase the activity. And in fact, we find that it's somewhat linear in terms of the CO, because the initial CO conversion is somewhat linear in relation to the partial pressure of the hydrogen and the activating gas. Now I was curious to find out what would happen if I activated in syngas under low conversion conditions, that is, activating in syngas at 270 degrees C at 13 atmospheres. Low activity for 93 hours. After that 93 hours, I decided to see what would happen if I stopped the hydrogen flow and treated the catalyst with just CO. So I did that, and after 22 hours, started back the hydrogen, and the activity dramatically increased, approaching pretty much exactly what we got when we activated with syngas, or with CO at 13 atmospheres. And I took catalyst samples before and after shutting off the hydrogen, and what I find is the inactive catalyst is essentially 100% magnetite, according to the XRD, and we verified this with Mossbauer. Now, catalysts following 22 hours of treatment with CO showed substantial amounts of pi carbide, the 8 carbide, and the epsilon prime Fe2.2C. So we took this as pretty strong evidence that the carbides are playing some sort of a role in determining the active catalyst. And in fact, what we find is that all of the catalysts that are active are converted to carbides, or substantial amounts of carbides, during the synthesis. And all the inactive catalysts, namely those pretreated at 13 atmospheres in syngas, are only reduced to magnetite. No carbides are formed. These are some Mossbauer results obtained on this is a 10-pound catalyst batch. It was pretreated in CO at 13 atmospheres and 270 degrees C. Now, at the end of the pretreatment with CO, we find that it's roughly 40% magnetite, maybe 38%. The remainder being a mixture of chi and epsilon prime carbides. Now, during the synthesis, the bulk phase composition changes dramatically. Essentially, the magnetite concentration increases, and the carbides drop down to about 16% superparamagnetic carbide. And this is happening while the conversion remains constant during this time. So even though the bulk phases are changing dramatically, the activity of the catalyst remains pretty much the same. So we're inferring this to mean that the activity of the catalyst is not based on the bulk phases, but probably the surface of the catalyst. And we've developed a theory of what we think may be happening, why the hydrogen partial pressure is influencing the pretreatment so much. After the catalyst is converted to magnetite, the associated carbon monoxide, the carbon that forms on the surface, can do one of three things. In the case of CO pretreatment, we know based on elemental analysis that we lay down twice as much carbon that is possible for stoichiometric carbide. So we're forming a lot of inactive carbon on the catalyst. Also, the surface carbon can then migrate into the bulk of the catalyst to form an active carbide, probably the Hague and the epsilon prime carbides. Now, in the case of syngas pretreatment, the surface carbon can be hydrogenated to form methylene and methyl species, which can then go on to form hydrocarbons, which we do see when we pretreat in syngas at 13 atmospheres. So what we think is happening is, when we pretreat in syngas under high pressure, the carbon doesn't have a chance to migrate into the bulk of the catalyst to form the active carbide species. Instead, it's being pulled off in the form of hydrocarbons, and it remains as an inactive hematite or magnetite. So we can conclude tentatively that we know that for sure the formation of carbides, namely the chi and the epsilon prime carbides, are necessary for initially high FTS activity. However, the iron carbide formation decreases with increasing hydrogen partial pressures of the activating gas. And we found that the best activation procedures is with CO. It doesn't matter if it's at high pressure or at atmospheric pressure, but if syngas, it must be done at 1 atmosphere or below. And we find that the FTS activity is not dependent upon the bulk phase composition of the catalyst, implying that it is probably a surface species which is responsible, particularly making surface carbide. And I'd like to acknowledge Rob Spicer for the work in the preparing the catalyst, and Yongzi Lee for doing the Mossbauer results, getting to the Mossbauer, and United Catalyst for helping us in the preparation of the large batch catalyst. And this work was funded by the U.S. Department of Energy and the Commonwealth of Kentucky.
When you sample from your slurry reactor, what size are your particles that you finally get out?
We start off with a catalyst size of about 60 microns, so that's what we shoot for. But in the CSTRs, they get beat up really badly, and we end up with about a micron.
They're pretty small. I was just wondering whether there was any way that you could do some depth profiling of what comes out to verify your idea that the carbides on the surface and the oxide might still be inside.
Right. Well, we're getting a high-resolution TEM on that, so we're hoping to find I made a slide for it, but I didn't put it up there because I didn't want to really get into it. But we're thinking it's something like this, that we're forming a magnetite core with like an eggshell of carbide around it. Just based on our Mossbauer results, we know that it's 16% carbide with long times on stream, approximately like that, the rest being magnetite. And we can conclude from the X-ray fraction data that the magnetite is about 250 angstroms, the individual particles. And if we base the carbide content on that and put it around the surface of the magnetite, we end up with a layer of about 6 angstroms. So it's consistent with the surface carbide, but we'll have to find out from our TEM results. Hopefully we will.
You showed a slow deactivation with time for the reaction.
Mm-hmm.
Could you check that surface effect by regenerating and then carbon monoxide treatment?
I'm not sure I follow you.
If after 2,000 hours CL.
You think you beat up the particles and
Right.
therefore eliminating the carbide shell.
Oh, okay. Yeah, that could be.
So somewhere through the reaction, after you see the deactivation, reform the carbide with another CO treatment.
It's possible. I haven't tried that. I don't know. I could try it. I've got a reactor running right now. It's when it deactivates. I'll probably try it.
Especially as attrition of the catalyst going in.
Yeah.